This is applied physics course for undergraduate students. Today's talk is about the laws of motion, and I'm Dr. Nasir Mirza. We will be discussing today laws of motion. This is taken from the chapter 3 of book Physics, Volume 1 by Halliday and Resnick. The laws of motion start with the idea of force. Everyday experience says that force is basically a push or a pull. For example, someone is pushing the cart to move it, or players are throwing or kicking a ball. Force is what causes any change in the velocity of the object. However, in physics, proper definition we are going to do, but force is, roughly speaking, which agent which causes an acceleration or really change in velocity as a function of time. There are classes in forces, and first class is the contact force. The contact forces are those forces where the physical contact between the objects is involved. For example, spring is attached to a mass and it is pulled. A cart is being pulled by a person, or a football kick with a high force is applied. Such forces are the contact forces. The field forces are those forces that act through empty space. There is no need for physical contact, and it is without physical contact. The examples are that a moon is attracted to Earth through gravitational force, and the electrons are attracted to nucleus of positive charge through Coulomb force. A magnetic needle points north and gets deflected in Earth's magnetic field, and it is magnetic force. The physics describes that whenever we try to study the motion, we want to study the objects and their motion with respect to position, velocity, and acceleration. And in this regard, we have gone through this, that the kinematic equations are in use. Kinematics is where there is no consideration of what is influencing the motion, what kind of forces are involved. We are really concerned about the motion and its results, that is in terms of the displacement, the velocity, or the acceleration. However, in dynamics, we study the effect of forces on motion, and the dynamics is where the laws of motion come into play, and forces are really balanced, and forces are studied. Two main factors that are needed to be addressed to answer such questions about why the motion of the object will change. The first is the force acting on the object. The force, whenever it is acting, it is actually causing acceleration and further changes in the motion. The second important factor is mass of the object. It is intrinsic property of the object, and the mass causes, again, the change in motion or the state of the system. So let's start with the three basic laws of motion that were formulated by Isaac Newton. Before we go further, let's briefly address the Newtonian ideas and Newton's work. Ancient physicists and philosophers did not really understood the motion of objects. They used to ask this question: do all motions require a cause? What if there is no relationship between the cause and the effect? And then was the point, what if the nature is there which is causing all this? So the confusion persisted until 17th century and was really removed by Galileo and Isaac Newton. They developed the approach to understand the motions of objects, and then the subject was termed as classical mechanics. Newton also presented his three laws of motion in 1687 in his famous book called Principia. Newton is also famous for spelling out the classical mechanics, which formed the basis to study all types of motions and the forces and the results of the forces. He formulated laws of mechanics that also led to the discovery of law for universal gravitation. He also invented forms of calculus and reported his work on light and optics. At this stage, there are known fundamental forces, four types, and the first one is the gravitational force, and it is due to the masses and the objects, and the force of gravity is between the masses, and it is related to the distance between the masses, and it is related to the mass of the bodies, and larger the mass, the larger is the gravitational force. And the first few ideas were put forth by Newton, and then later on Einstein formulated his general theory of relativity, and spelled out that gravitational forces are really manifestation of the curvature in space due to the high and heavy objects. And the curvature of space leads to this intrinsic force, that is a gravitational force. And the sharp gradients do cause the increase in the gravitational force, and gravity can be very severe around heavy masses. When the mass of the object is very, very high, it can get converted into black hole, and black hole are those objects where the curvature is steep and gradient is so high that even light cannot escape the force of gravity. Later studies by Stephen Hawking on the black hole have led to further understanding on gravitational forces and further explanation on the waves that are related to this gravitational field. Gravity acts at a distance, and now we know that the gravity is truly a manifestation of the curvature. A deep curvature in space. Space is not so flat as we see around for the small masses. Electromagnetic forces are those forces that are between the electric charges, and it's all due to the charges. The motion of charges or the stationary charges do cause electromagnetic forces. Electromagnetic force is basically a combination or what we call the unification of the electric force and the magnetic force. And Maxwell wrote down this unification. The electromagnetic force combining together these two forces have led physicists to find further that is there a possibility to unify all forces. The next important force is the strong nuclear force, and it is between the subatomic particles, and it acts for very, very short range, and the nuclear force is what is keeping the nucleus in a bounded form. Weak nuclear force is also arising within the nucleus, and it is the reason for certain radioactive decay processes such as beta decay. The weak nuclear forces have also further led to scientists to discover the principles of the unification, and now we know that weak nuclear force is also at very high temperatures can become electromagnetic force. It is actually manifestation of electromagnetic force, but at a short range. The weak nuclear forces unification was done by Dr. Abdul Salam and Sheldon and Glashow. And now there is huge work going on to unify all forces together, including the gravitational force. When we talk about the forces, the forces can be used for the calibration of the instruments, where the magnitude of the forces are expressed in certain other relations. For example, this is a spring which is used to calibrate the magnitude of the force, and let us say that a force F1 is applied on this first spring and its elongation is 1 centimeter, as the red mark is shown. When we double this force, that is F2 is the twice the F1 force, then we see that this mark, the reading on the spring elongation becomes 2 centimeters, and it is the double, twice the value that was with the first spring. Now, if we apply both F1 force and F2 force together in downward direction, in the same direction, then reading becomes 3 centimeters on this spring as compared to the initial reading. So we can say that the force is acting, and it is directly proportional to the elongation, and the elongation can be used to measure the force. There is also vector nature of the force, that the forces are dependent on the angles where they are applied, and there are the resultant forces, and you can see here a resultant force F is here, which is elongating this spring, but at angle theta with respect to the horizontal axis. And the components along the x direction and the y directions are shown as F1 and F2. And if we combine the vector sum of these two forces, will lead us to the resultant vector. So forces are vectors. We can say that we can use the laws of vector addition to find out the net force acting on an object. In classical mechanics, we focus our attention on particular object which interacts with the surrounding objects, so its velocity changes or acceleration is produced. So central problem of the classical mechanics is that an object with the known physical properties, such as mass, volume, electric charges, and other properties, are placed at a known initial location with the known initial velocity. Then we can measure all the other interactions of this object with the environment. We can also predict the subsequent motion of the object, and we can also find the position and the velocity at all future times. So it is this prediction that is really admirable in classical mechanics. For this analysis, we treat physical objects as particles who are having internal structure or motions, but we ignore those, and we consider that all parts of the object are moving exactly the same way, and we can treat it as a point particle. And for classical mechanics, the objects are treated as particles, particles with mass, particle with the point objectivity, and we can ignore about the structure and the rigidities and the other things of the particle. Here are some motions, some accelerated motions, and we we compare and try to state what kind of forces are there. If apple is falling from the tree, the environment is earth and the type of the force is gravitational. And if car is coming to stop on a road, then there is a frictional force on the road which supported this application of deceleration. If there is a compass needle and it is rotating towards north, then Earth environment is causing this, and the magnetic field of Earth is responsible for this effect. So force is magnetic force. Beam of ink drops in the printer, and it is really due to the deflection, deflections, and the motion is deflection motion. But the capacitor, the action of the capacitor is responsible for this, and the electric force is really the reason for this deflection. Helium balloons are seen rising from the land in air, and the environment is air, and the force is a buoyancy force. It is the density difference which makes the application of the force, and space likes to fill the empty positions, and the helium balloon flies up in the air against the gravitational force. Again, we look at the term force. We actually describe the force in terms of the interaction of body with its environment. And the force is a really push or a pull in the particular direction. Forces can be described using vectors. For every force, we must specify direction in which it acts, and the forces must be combined using rules of vector addition. We have considered mostly situations involving one-dimensional motion in which the force component, positive or negative, are related to one direction. And we assign the force positive directed towards the right side and the negative towards the left side. The Newton's law of classical mechanics were formed and they form the basis for our understanding of motion and its causes in terms of forces. Each force is exerted by an object that is causing it. A particular body in its environment is then pushed. For example, pushing a force on a crate by workers, or the frictional force on a crate by floor, or gravitational force on a crate by earth. So forces and laws go together. A body in the environment is really responsible for the force. So we define the magnitude of the force in terms of acceleration. Acceleration of a particular standing body. We develop forces and force laws based on the properties of the body and its environment. Force is thus appearing in both the laws of motion, which tell us that the acceleration of the object will be experienced under the action of a given force. And the force laws are there, which tell us how to calculate the force on body in a certain environment. So if you look, the force laws are really imposing things in environment, force, and body. However, the laws of motion are really responsible for telling that if there is a force on a body, then it is going to cause the acceleration. Let's talk about the first Newton's law. This law is really adopted by the Newton as the first of his three laws of motion. The statement is that consider a body on which no net force acts. So this law starts with the negation. If there is no net force, then we say, if body is at rest, it will remain at rest. If body is moving with constant velocity, it will continue to do so in the absence of any net force. So what we are saying is that force is needed to set body in motion, but if no external force is there and body is moving you can keep on moving body with a constant velocity. There is no need for any external force. Force of gravity acts on object near Earth, and the resistive forces such as friction in air or friction of the surfaces or the air resistance opposes the motion on the ground or in the air. So the net force remains less. For overall translation motion of the body, there is no distinction between a body on which no external force acts and a body on which the sum of the resultant forces is zero. So if we don't see any force or a no net force, then if body is at rest, it will remain at rest. If body is in motion, it will remain in motion. We generally refer to the resultant of all forces acting on a body as the net force. However, remember that the law of addition of vectors says that the resultant is actually the end product or the addition of the vectors. So either vector in positive direction or in a negative direction or many possible directions, we have the net force as a resultant of all forces. The Newton's first law has another alternate statement, that is, in the absence of external forces, when we don't see any net force, but when it is viewed from an inertial reference frame is, we are going to interpret this frame in coming slides. Then object remains at rest, will remain at rest, and an object in motion will continue to move with a constant velocity. So Newton's first law describes what happens in the absence of a force. However, it does not describe the zero net force. Also, it tells us when there is no force acting on an object, the acceleration of the object is zero. It can keep its state as such. We can also conclude that an isolated object is either at rest or moving at a constant velocity without any hindrance. The first law actually gives us the definition of force. That is, it causes the change in the motion of the object, or it causes the change in the state of the object. If it was at rest, it will remain at rest if there is no force. If it is uniform and constant velocity, it will remain uniform and constant velocity without any force. So let's consider this reference frame now. For each observer, such as you sitting in a car or traveling on an aeroplane, your friend standing on the ground and the pilot in the aeroplane will define the reference frames. All of them have their own frame of reference, the coordinate axis. The reference frame requires the coordinate system and the set of clocks that are going to enable observer to measure the position, velocity, acceleration, and time in his particular reference frame. Observers in different reference frames will measure the different velocities and accelerations. So Newton's first law is very important. It helps us to identify a set of specialized reference frames in which we can apply the laws of the classical mechanics. Let's see how we are going to interpret the Newton's first law using the idea of the inertia. In general, acceleration of the body depends on the reference frame relative to which we are going to measure. However, the laws of the classical mechanics are valid only in certain set of reference frames. For example, all those observers would measure the same acceleration for a moving body if they are in certain reference frame. Newton's first law allows us to choose this specific family of reference frames if we express it like this. If the net force acting on a body is zero, then there is a possibility to find a set of reference frames in which the body has no acceleration. Once we find those reference frames where there is no acceleration, then we can use that as our reference frame. The tendency of the body to remain at rest or to be in uniform linear motion, it is called inertia. So inertia is the state's, you want to keep the state of the system as such. So Newton's first law is basically all about the inertia. It is telling us that system would like to keep its inertia in the absence of any external force. So that's why the Newton's first law is also called the law of inertia. And all those frames where there is no net force acting on a body and there is possibility that the body has no acceleration as such, then such a frame of reference is inertial frame. Let us compare the inertial frames. Any reference frame that moves with a certain velocity which is constant relative to another frame is inertial frame. Here we show one frame in a black form, and that is really at, we are trying to say that it is at rest, and the other frame of reference with the blue color is moving with velocity v. This velocity is with respect to this frame. So if you accelerate the relative to an inertial frame, then you are observing the object in a non-inertial frame. If this frame starts accelerating, then we are seeing this as a non-inertial frame. A reference frame which moves with a constant velocity relative to distant stars is the best approximation for an inertial frame. Roughly speaking, we consider Earth to be also an inertial frame, although very small centripetal acceleration is associated with the motion of the Earth. But generally, the smaller values of the velocities and for the smaller values of accelerations, Earth is also sufficient to be called as an inertial frame. Now we come to another important conclusion, and that has to be drawn based on the observations. And it is related to the mass and the relationship of the force and mass. So according to the Newton's first law, the absence of forces will lead us to the absence of accelerations. So what about the presence of the forces? If there is a force present, so based on our common experience, we assume that body will get accelerated when a force is applied. So presence of force is really in terms of the acceleration in body. It is also clear from the measurements that for when we start combining the bodies together, the acceleration is directly proportional to the force. For example, for a case of 2 units of force will give the twice acceleration as the 1 unit of the force will give. So acceleration keeps on improving or increasing as we keep on increasing the force. This proportionality constant between the force and acceleration, however, is different for each case, and it is the characteristic property of the object that is accelerated. The property of the object is mass. So mass gives the proportionality between the force and the acceleration. So we can conclude this from the experiments that there is a marked relationship between the force, the mass, and the acceleration. Other experiments also show us that the mass and acceleration are also related to each other. The tendency of an object to resist any attempt to change in its state or velocity is inertia. And the mass is the property of the object that specifies how much resistance of the object is to exhibit the inertia for any change in its velocity. Masses can be defined in terms of accelerations and the accelerations produced. When we consider two objects, for example, m1 mass and m2 mass, and we apply a given force F to m1 and the given force F on m2, and then measure acceleration as a1 and obtain acceleration as a2, then the ratio of the masses m2 divided by m1 is really equal to the acceleration in the first object divided by the acceleration in the second object. The force is same. However, we see here that the ratio of the mass of the two bodies is the same as the inverse of the ratio of the acceleration. So mass is inversely related to the acceleration. This observation gives us a direct way to compare the masses of different bodies. If we apply same force to two bodies and we measure resultant acceleration, we can start measuring the mass. So idea of mass as an intrinsic property of the object comes from inertia, but the way to measure is by comparing the acceleration which occurs for the same force. And we know very well that the mass is inversely proportional to acceleration, or acceleration is inversely proportional to mass. Such studies in the times of Newton led him to the second law of motion, and then he combined these two ideas together, that the force is directly proportional to the acceleration produced in object. Larger the force, the larger is the acceleration, and the proportionality constant is mass, but mass is inversely proportional to the acceleration. Larger the mass, smaller is the acceleration. If acceleration is large, the mass is small for the same force. We can also use the ratio of masses of the two bodies to find out the possible resultant acceleration, and we can compare the masses. We can always use this kind of a ratio which has been employed. In initial slides, we have already shown you that the force and the elongation of the spring are directly related to each other. So elongating a spring with the help of a force is really indirectly a measure of the force. And then we can use the masses and the accelerations ideas to find out the ratios. So we stop here and we will continue our discussion in next lecture on the Newton's second law. Thank you so much.